Hello there, welcome to part 2 presentation on handling non-homogeneous ordinary differential equations using the methods of undetermined coefficients. At this stage, we are actually dealing with equations, ordinary differential equation of order n of this form where an is different from 0. We recall that in the case that the right hand side of x, the right hand side of the equation f of x equal to 0, we are talking of homogeneous differential equations. On the other hand, if f of x is not equal to 0, we talk of non-homogeneous differential equations, which we are doing with now. And we recall that also we said the f of x could be any type of these functions: polynomial, trigonometric, exponential, or a combination of the above. So in the previous presentation, we looked at examples of the following type. For example, example 1, we've seen how we handle homogeneous equations. And on the simplest case of non-homogeneous, we considered where the f of x, the right-hand side, was a constant. For example, f of x equal to 5. And what we actually dealt with in the previous presentation was how to handle the equations when the right hand side was actually a linear function. In this presentation, what we're going to do, we're going to look at how we handle quadratic functions. In other words, when the right hand side is a quadratic function, is a cubic function, and so on, in which case we should be able to figure out after that how we can handle a polynomial of order n given on the right hand side of the equation. So in the list of exercises which I gave you, I actually challenged you before dealing with this that you try to figure out how we could handle this type of an equation. We're actually going to solve this as our example, as our first example today. Actually, at the end of this presentation, you should be able to handle any of these equations and also be able to figure out how you can actually handle higher order differential equations with the right hand side being polynomials of order n, in this case n greater or equals to 2. In this discussion, we're going to go as far as n is equal, the order of polynomial here is equal to 3. So in this case now, we've got to look at examples. For today, I'm going to look at example A and example H, at the end of which we will be in the position to solve any of these exercises and also figure out how you can deal with the equation of any order n with a polynomial here of n order n. Moving forward, let's look at the following example, which was the one which I left for you as a challenge, which we're supposed to figure out how to deal with it. So in this case, simply solve the second order differential equations. And now we note that right hand side here, in this case now, is not f of x, but it's an f of t, which is a polynomial of order 2. Now solving this, we'll do the following. So like we said before, our initial step will be to extract the characteristic equation for this differential equation, which will come out as m squared plus 4m plus 5 equal to 0. Now, to solve this characteristic equation, like already we know how to use the roots to get the characteristic solution. We know, first of all, note that this quadratic expression cannot be factorized. Then we're going to resort to the formula, which in this case we're going to say m1, 2 is equals to minus 4 plus the square root of b squared, which is 4 squared, minus 4ac, which gives us minus 20, all over 2a, where our a is equal to 1. Then we get this as minus 4 plus minus square root of minus 4 all over 2, which you all see that this simplifies to minus 2 plus minus I. So we've got a complex root there. Then we know that our characteristic solution here is going to be xc, a function of t, which is going to be given by e to the power minus 2t, which is our a in this case here, our real part here, brackets, capital letter A, cosine, with an angular velocity which is equal to 1, which is the coefficient of I here. So 1t, right, t, plus b sine of t. This, of course, you've got to go back and revise how we handled the complex solution in order to get characteristic solutions. Now, having that, our second part will be to get a trial solution. So let's say trial solution. So we say let our trial solution in this case, which is going to be x p particular integral, a function of t. Like we said before, we said in this case, if the right hand side is given, previously we said if the right hand side was given as a linear function, so in our trial solution we were to suggest a linear function. In this case here is a quadratic function. Likewise, we're going to suggest a trial solution to be a quadratic expression, which is going to be x particular integral a t squared plus b t plus c, which is the general form of the quadratic function. But now notice that this trial solution, we will use it even if we only had f of t equals to t squared, or f of t equals to t squared minus t. I hope you see what have happened here. Here, this is a one-term quadratic function whereby our b is 0 and our c is also 0. And this on this side, we've got our a being 1, we've got t squared, and our b being minus 1, and then our c being 0. So whatever type of never mind how many terms you've got in the quadratic expression here, your trial solution, you will always suggest this general form of a quadratic expression. Now moving forward, now we assume that this is a solution. Our particular integral is a solution to differential equation. So what we're going to do now, we're going to get the first and the second order derivative of this function. So getting the first derivative, we'll say x prime, that will give us 2a t plus b. And then the second order derivative of the particular integral will give us 2a plus 0, which is that. Now, since this is a solution, we assume that it satisfies the equation which is given here as second derivative plus 4 times first derivative plus 5, the solution times 5 times the solution x. So what we're going to do now, we're going to take the second derivative, which is this one, which is 2a plus 4 times the first derivative, which is going to be 4 times 2a, which is going to be 4 times the second derivative, which is going to give us 8at plus 4b. and 5 times x according to the equation, and this is our x, so we're going to get here plus 5at squared plus 5b plus 5c. Please note that here what I'm doing here, I'm actually mimicking the left hand side of the differential equation, which is given here as it's given there. We've got the second derivative plus 4 times the first derivative plus 5 times the solution x. This is what I've done here. So then adding this, what we have here, we see that we've got 5at squared plus 8at, which is our linear term, plus 5bt. There's a t missing here. That is our linear term, plus 2a plus 4b plus 5c, which is our independent term. So this is the left hand side of the differential equation, and the right hand side we're given here as, the right hand side is given here as t squared plus 5t plus 20. So if here we've got t squared plus 5t plus 20. We expect that equation to balance because we assume that the particular integral such as here is a solution. So comparing coefficients here, we see that 5a is equals to 1, which is the coefficient of the leading term there, which simply gives us that a is equals to 1 over 5. And then next we've got here 8a plus 5b, which is our linear coefficient here, is equals to 5. And now knowing that a is equal to 1 over 5, which means here we've got this giving us that 5b is equal to 5 minus 8 over 5 by multiplying this 8 times 1 over 5. So simplifying this, we've got here 25 over 5, which is 5, minus 8 over 5, which gives us here 17 over. Now dividing both sides by 5, we get here that b is equals to 17 over 25. That's what we've got for b. Now we are supposed now to get c, and the c is the independent term, which is the sum of 2a, 4b plus 5c. In this case, we're going to have 2a plus 4b. In this case, 4b, b is 17 over 25 plus 5c plus 5c, and the 5c in this case is our known, and our a here is 1 over 5, so we can substitute that. We get here 2 over 5, and then this is our independent term, which is equals to 20, which we have there. So simplifying this, what we're going to have here, we have got to multiply 4 times 17, which gives us 28 carry 2, and that is 68. That will give us 68 over 25, and this side, this will give us 10 over 25, and adding there we get 78 over 25. So we've got here 5c equals to 20 over 1 minus 78 over 25. And you can simplify this using a calculator. Let's see what it gives us. Simplifying this using a calculator, it gives us that C is equals to 3.376. So now we have got all our unknowns A, B, C. A is here 1 over 5, which is simply 0.2, and B is here, which you can write as we can write as 0.68. So now we can write our particular integral as xpi, a function of t, equals to A, which is 0.2 t squared, plus B 0.68 t plus 3.376. That's our particular integral. So now we have got complementary solution, and our particular integral, we can now write the general solution, which is xg, whereby we are going to add our complementary solution to the particular integral, which gives us the following. We've got our complementary solution as follows. So we have here this as equals to e to the power minus 2t, the undetermined coefficient a cos of t, plus an undetermined coefficient b sine of t, plus the particular integral here. In that way, our general solution will be complete, and only when we are given the initial conditions, then we'll be able to determine these undetermined coefficients and then obtain a unique solution. So I hope you have seen how we have handled our first right hand side, which is not a linear function but a quadratic function. Now moving on to the next example, which in this case, now the right hand side is now a quadratic function, which is 2t cubed plus 8t squared plus 2. So the solution in this case will be as follows. Again, our initial step will be to extract the characteristic equation for this differential equation, which is going to be m cubed plus 3m squared plus 4m plus 2 equals to 0. So one thing here which is not been said but it is clear is that our knowledge of factorizing or solving equations of order n is going to be important here, whether it's by factorization or sometimes using the quadratic formula, or factorizing cubic expression, quadratic expressions, and even expressions of order 4 will be very important. But in this module, we are going to go as far as the polynomials of order 3, hoping that will help you to figure out how you deal with characteristic equations which are of polynomial order 4, 5, and 6, and so on. So in this case here is a characteristic equation we need to solve. Now, first of all, it's not very easy to figure out that how can we factorize this expression, but we can appeal to theorems like factor theorem and see whether that can help us. So, for example, in this case, let's try m equals to minus 1 to be a solution to this polynomial. Remember, if m equals to minus 1 is a solution to this quadratic equation, then we know that m plus 1 is a factor of this polynomial. So what do we do then? We substitute minus 1 in this quadratic equation. We get here minus 1 plus 3 brackets minus 1 squared plus 4 minus 1 plus 2. Simplifying this, what we see here, we get you get here 3 plus minus 1 plus minus 4 plus 2. So 3 plus minus 1 gives us 2. 2 plus 2 gives us 4. 4 plus minus 4 gives us 0. So now this tells us that m plus 1 is a factor of this quadratic expression. So that way now, what we do, we then divide this expression by this factor, which is m plus 1. Then we've got m cubed plus 3m squared plus 4m plus 2. So this will be a very useful skill in this case. If you don't know it, you better recap it. That is in case if you've forgotten it. So what we do now, we're dividing m into m cubed here we get m squared, and then multiplying we get m cubed plus m squared, and the subtracting here we get 0 there. Then there we get 2m squared plus 4m plus 2. Now dividing this by m, we get the 2m, and then multiplying this 2m by this factor, we get 2m squared plus 2m. Subtracting 2m squared minus 2m, we get 0, and then here we get 2m plus this 2. Now dividing this m into 2m, we get plus 2, which gives us 2m plus 2, making here the remainder 0, which means effectively this is that. So this polynomial is supposed to be m plus 1 multiplied by this quotient here, which is m squared plus 2m plus 2 equals to 0. Now from here we can conclude that m is equal to minus 1, like we tested, and then we're left with m squared plus 2m plus 2 equals to 0, which again we can solve using the quadratic formula because this is not factorizable. Then we get here m1, 2, which is equals to minus 2 plus minus square root of 2 squared, which is 4, minus 4ac, which gives us minus 8, all over 2. And when we note here that we get minus square root of minus 4, which is 2i, plus minus 2i. So we've got here minus 2 plus minus 2i all over 2, which gives us minus 1 plus minus I. In this case, we've got a complementary solution again, which we get from this complex roots, which is going to be e to the power minus t brackets a cosine t plus b sine t, which is our complementary solution. Now, the next step now is to suggest a trial solution. Like we've seen, the right-hand side is a cubic function. Then we'll suggest a trial solution to be a cubic function, and we'll take it in its most general form, which is in this case going to be x pi of t, which is going to be a t cubed plus b t squared plus ct plus d. That's what we're going to use our trial solution. So moving forward, we have here x particular integral function of t being a t cubed plus b t squared plus c t plus d. So now you know that when you've got polynomials on the left hand, on the right hand side of these differential equations of order n, the trial solution will always be a polynomial taken in the general form. Let's say if it's a quadratic, you take a general form of quadratic equation, which is a squared at squared plus bt plus c. Now it's a cubic, we're taking the general form of a cubic expression, which in this case a t cubed plus b t squared plus ct plus that. You should never overlook that, because otherwise that presents problems. So now we don't have to lose sight of the left hand side of the equation, which is this one. Now looking at the left hand side of the equation, we see that we need first the function. In this case, we have used x here. This is y. So let's correct that. So you have here yc, complementary solution, and then here y, particular integral. Now having that now, needing the first derivative, the function, this first derivative, and second derivative, and third derivative, this is what we're going to do. This is what we're going to do. And all these are added. I'm going to simply write here plus. So what I'm going to start by, taking twice the solution which is suggested there, which is going to give us 2a t cubed plus 2b t squared plus 2c t plus 2d. That captures this part of the equation. So the next thing, I need 4 times the first derivative. So I'll write here 4 brackets. The first derivative will be derivative of this expression, which will give us 3a t squared plus 2b t plus c, and then next we'll add 3 times the second derivative. Then we write 3 brackets, differentiating this first derivative, we'll get here 6a t plus 2b, and then plus the third derivative, which is actual derivative of this, which is going to give us 6a. Now we need to simplify this. This is the left hand side. We need to simplify this and match it with the right hand side there. What we're going to get actually is the following. The first row there is 2a t cubed plus 2b t squared plus 2c plus 2d, and then we've got 12a t squared, 12a t squared plus 8bt plus 4c. If you check what I'm doing here, I'm just simply mimicking the left-hand side of the equation, but I'm trying to match the like terms so that I get my work a bit organized and easy to follow. And then coming here, I would now multiply this by 3. I'll get 18at plus 6b. And then lastly, we're going to have here 6a. Now, if we check now, if we say this is equals to the right hand side here, which is 2t cubed plus 8t squared plus 0t, because the linear term there does not appear, so assume the coefficient is equal to 0 plus 2. So what does this tell us? This tells us that the coefficient of the cubic term here is equal to the coefficient of the cubic term there. So which means 2a is equals to 2. Conclusion, therefore, a is equals to 1. Now coming to the quadratic expression, what we have here, we've got 2b plus 12a. 2b plus 12a equals to 8, which is our coefficient for the quadratic term. But already we've got that 2 here is a here is equals to 1, which means what we've got here, we've got 2b equals to 8 minus 12, which gives us minus 4. And looking at these two, we conclude that b is equals to minus 2. Now coming to the linear term, we now have got b and a, and here we've got 2c plus 8b plus 18a, 18a plus 8b, 18a plus 8b plus 2c. That is our linear term, that is equal to 0. But already have got here that a is equal to 1, so this means that we've got 18 plus b is equals to minus 2, minus 8 comes minus 2 plus 2c equals 0. Got 18 minus 16, which is a 2. And then we've got here 2c equals to minus 2, where we can conclude that c is equals to minus 1. Now we are left with d. What we have here is that 2d plus c is minus 1, so we've got minus 4 there. Minus 4 plus b is minus 2, then we've got minus 12 there, and the a is equal to 1, then we've got 6, all that equals to 2. Now simplifying this, we've got 2d minus 12 minus 4 is minus 16, plus 6 minus 10 equals 2, then that gives us that 2d is equals 2 plus 10, which is a 12, therefore d is equals to 6. So we've got all our constants here. We've got b there, c, d, and our a is 1. So now we can write our solution as y particular integral, a function of t, is equal to t cubed minus 2t squared minus t plus 6. That will be our particular integral. Now coming to the next step, which is now step number 2, we need to now give our general solution, which we're going to write here as yg, a function of t, which will be this particular integral, y pi plus y complementary both functions of t. So we can write here t cubed minus 2t squared minus t plus 6, and we saw our complementary solution was e to the power minus t in brackets a cos t plus b sine t. So in this case now, I think you have seen the whole process of solving, in the first example, a non-homogeneous equation when the right hand side is a quadratic function, and now here we've seen solving a non-homogeneous third order differential equation having the right hand side being a cubic function. So most important is the fact that whenever we look, in this case of when we are dealing with polynomials, we must look at the order of the polynomial, which is on the right hand side. Then when we suggest a particular integral, we suggest a particular integral which is of the same type in its most general form. So having these examples, I think now you can be able to deal with the problems which we have listed here. Any of them, you can see I've give you the quadratic second order differential equation and the third order differential equation. And from this, you should be able to figure out how you are going to deal with equations of fourth order and fifth order and so on. And in some cases, for factorization, you might even need to use MATLAB just to simplify tedious calculations. At this point, I would like to urge you to do the practice, look at the exercises which I gave you, and go through all of them. At this point, I would like to say thank you for listening. My name is Charles Wasfani Msipa.